welcome to ML Done. This is Mehran. Today I want to talk to you about some of the most, common and yet confusing parts of machine learning that in my time I found most people to struggle with. And the funny part about this is that these concepts are basically quite common and the very foundation of the most complex models that people are running around the world. Anybody who's dealing with machine learning, they use all these error functions in their neural networks, but unfortunately they have not the best understanding as to why these error functions work, why certain error functions would work better with certain architectures, why certain output functions in the neural network would be better with certain error functions, that they would pair well. If you tell them that I have a neural network and I want to say solve a binary classification problem, and if you ask them to tell you about which error function to choose, they would immediately jump into binary cross entropy function. And if you ask them, okay, what would be the output unit function, the nonlinearity that you would have in the most outer layer of your neural network, they would immediately say sigmoid. Okay? But if you ask them why that's the case, I don't know about you, but in my time, most people that I've asked these questions from, they don't understand why that is the case. And why that is important is because if in the future you wanted to become creative, if you wanted to propose a new algorithm, if you wanted to basically tweak certain algorithms and improve them, it's not possible unless you have a good understanding about the foundation. Right, let's talk on more work. So in this video, we're going to talk about the Bayesrule and the idea behind the prior probability, the likelihood, and the posterior probability. I'm not going to dig into details of Bayesrule. It's very well documented on the internet. I'm sure that you can just go and read about that. What I'm going to focus on is how the Bayesrule will be connected to generating the error functions. But I'm going to have a cursory overview of that. And then I'm going to talk to you about the maximum posteriori estimate, or MAPE, and how it can be translated to MLE, the famous maximum likelihood estimation. And then I'll talk to you about how we can pair this with the idea of supervised learning. And by the way, that is how we will basically enter the realm of error functions, because that is because that's where we're going to talk about how we can use these MAPE and MLE methods to basically apply them to the artificial neural networks. And finally, we will talk about the likelihood assumptions that we will be having, namely we will discuss the linear case, binomial case, and multinomial case. Well, this one might seem a little bit vague right now, but as we go on, you'll figure out what I mean. Anyways, now, the Bayesrule. Let's assume the following notation. So when I say M, I mean our model. So when we're talking about a neural network as a model, when I say M, I basically mean the parameters of my model, say the weights that you have in the model. And D means our evidence, basically our data. So it could be the output that your neural network is generating. Okay? So after introducing the notation, let's just talk about the Bayesrule for a second. So Bayesrule is basically a mixture of certain probabilities. This guy right here, we would call this the posterior probability. It is the probability of our model M being correct after having seen the data or the evidence. Okay, so after seeing my evidence, how much am I confident into my model? And that how much will be expressed by probability. Okay, and there's a way to compute this posterior probability. It's a mixture of three elements here. Number one, this guy right here is called the likelihood. Right. What does it mean? If you basically look at it, it's kind of the reverse of the posterior. So it is the probability of evidence given M. So it means that if I assume that my model is right, it's the correct model, what is the probability of observing D? For instance, what is the probability of observing a certain output? Okay? And this guy right here, which is not a conditional probability, this is called the prior probability. It is the confidence that I have in my model without giving basically giving a damn about my evidence, right? So basically what is the probability of model M being true? And finally, this guy right here, they would usually refer to this as the evidence. I know I used the word evidence previously for D, but basically D is, say, the data, the observation. Yeah, that's better. D is the observation. Pure notation there, by the way. Anyway, sorry. So P of D is the probability of seeing that particular observation, and it doesn't care about the model. Please note this, that this does not depend on our model. Lovely. So basically, after focusing on this one, now we're ready to jump into the next part where we will kind of manipulate this guy. Right. Usually what they do with this formula, they would take the log of both sides. And the reason for that is that we got loads of multiplications here, we got a division here. So log basically gets rid of the multiplication and the division. And it simplifies everything. You'll see what I mean by simplifying everything, because we're going to do a lot of work in here actually throughout this, this course. So bear with me for a second, please. So if I take the log of basically both sides, that would be the log of my posterior, which is the probability of my model being true given observation D. That equals, now I'm going to take the log of this guy right here. So basically it's the log of something divided by something. We know that from the math that log of A divided by B can be written as log of A minus log of B, right? So this guy right here would be, so this guy right here, the denominator is A, and this guy right here in my notation is B, right? So if I want to use this rule, say rule number 1 in here, I'm going to say log of A, which is log of denominator, which would be log of, denominator is the probability of observing D if my model is true, multiplied by the probability that my model is true without giving a damn about the evidence. So that's log of A minus log of B. So this right here, the evidence, is my B. So log of B, which is the log of the probability of observing D. Right. Now, about this guy right here. We know that, let me change color, it's too much white here. We know that log of A multiplied by B equals log of A, this time plus log of b, right? So I'm going to use it here because we have a multiplication of two probabilities here. Now in this notation, this is A, my likelihood is A, and my prior, the probability of model being true, is B, right? I'm going to break this guy into pieces now. Right, switching to white. Now, the log of probability of my model being true given my evidence equals. Now, this guy will be broken into log of A plus log of B. So this would be log of the probability of D given M, or the probability of my likelihood, plus the log of probability of my model, right? And the last term would just remain as it is, minus log probability of data. Perfect. Now let's remember this whole expression here, because we will deal with this later on. But a little bit of explanation here. This likelihood right here. So if you remember here, when we say the posterior, it means that what is the probability that my model is true given the observation D, right? The likelihood is exactly the reverse. It's like, okay, I'm gonna give you a chance. Let's just say your model M is true. If it were true, what would be the probability of observing D, right? Basically, what is the likelihood of your model being true? Okay, that is the basically the English version of what likelihood is. But anyways, this likelihood right here is a probability. How can we compute that? Because remember, ultimately what we're interested in is the posterior, right? Ultimately, you're interested in knowing, okay, what is the probability of my model being true given my evidence? Because eventually what you're interested in is to actually figure out how much confident I am in my model that I've been training and training and training for days and weeks and weeks and weeks to meet a deadline for a conference or whatever. Okay, so in order to compute that, we need to compute the elements, one of which is the likelihood, and then the other one is the prior of your model. The other one is the evidence, the probability of your data of the observations. Okay, so how can I compute likelihood? This can be dealt with easily if your model can compute the probability of an observation, right? So if your model can automatically just compute this probability, for instance, if in your multi-layer perceptron network, in your artificial neural network, you have a softmax function in your as your output layer, they can be interpreted as probabilities, because as you know, the sum of those guys, the sum of each output neuron of your neural network, if you sum all of them up, you would get 1. Okay, so each one of those elements could be considered, could be interpreted as probability. Okay, so that is one way to deal with this. The other one would be if the model generates data with a certain probability. Okay, like restricted Boltzmann machines. Okay, which is a generative model. Now, in an artificial neural network, we use error functions to evaluate how well our model is doing, right? So basically, the question is, how can we translate this likelihood into an error function, right? Because we're going to use these likelihoods to express, to eventually basically compute our posterior. So we're going to find a way to deal with the connection, or make a connection between the likelihoods and the error, okay? We will need to make some assumptions on how the error is distributed. Why? Because I'm gonna compare my error with the likelihood, which is a probability, right? So whenever you're talking about the probability of a random variable, you're talking about the distribution of that random variable, right? So that is why we're gonna deal with the basically distribution of our error. Now, let's see. So in order to do that, we're going to talk about the Bayesian missionary to basically reach to something called MAPE. I'm going to talk to you about this in a minute. Remember that we said that our posterior, the log of the posterior, equals, so the log of my posterior, just a reminder, equals log of my, oh, this looks really bad, sorry. Yes, so this equals the log of my likelihood, given m, plus the log of my prior minus the log of my observation. Right. So if I want to use this and kind of like, in a way, define an error function out of this, what we're trying to do here is we want to find a model that maximizes this probability, okay? Which in turn would maximize the log of that probability, because remember that if you say that at this particular point function f of x is maximized, that point is exactly the point that would maximize the log of that function as well. So that log over there does not interfere with our optimization at all. It's just there to simplify the computation. That's all that it is, okay? So we want to maximize the posterior, okay? Basically, if I want to kind of translate my language into basically errors, I can say that if I were to say multiply all of this into a minus, namely the minus of log of my posterior, that would be equal to minus log of the probability of d given m, or my likelihood, minus the log of my prior probability, plus the, sorry, I made a mistake here, p would be here, I missed that, sorry, plus the log of probability of observation, right? Now, in machine learning, we call this E, or our error. Why? Because previously we said that, okay, we want to maximize the posterior, meaning that I want to find the model for which I am absolutely confident that that is the right model, right? So when you deal with errors, you're always talking about minimizing the error, minimizing error. So just for the terminology to make sense, we would multiply everything by minus. So basically maximizing the posterior, or maximizing the log of posterior, equals to minimizing the minus of log posterior, right? So they're both the same thing. So when you, now that I'm talking about minimization, now I can say that, okay, this guy right here, this whole thing is an error function. So is the right-hand side, right? So basically, whenever we're talking about just posterior, and we're talking about maximizing the posterior probability, we're talking about something called MAPE. So if I want to show what it means, so MAPE, stands for maximum, that's a cute color, a posteriori estimation, or MAPE. Okay, so we basically minus everything, multiply everything by -1, and we get the error function. Cool. So the idea of error function is gradually coming out. Lovely. Now that we know that our posterior equals this whole expression, just as a reminder, I want to keep repeating this so that we would not lose connection. The likelihood, the given m minus log of our prior probability, and plus log of p of d, right? Remember, I've multiplied everything by -1, okay? Now, we want to maximize basically our posterior, or basically minimize this whole thing, this whole error. Okay, so if I put e here, yeah, so this is my error function that I want to minimize. Right now, of all of these, this guy right here, the probability of observing d, this guy right here does not depend on my model. There's no interaction between this d and my model here, right? It is independent of that. So if I want to maximize basically or basically minimize this error function, and I want to find the best model ever, this right here is not dependent on my model, so I can just get rid of that and do not consider that during maximization. Okay? So the error function consists of my prior probability and the likelihood. Okay? Now, it is common practice to sometimes, basically during maximization, during minimization, not consider the priors. You know, if your prior is uniform over all the models, or some people just say, well, we don't like it, we don't want to have it, then we can just consider the likelihood on the right side, meaning that you can also ignore that. Okay, because you know the use of priors is largely criticized in the literature, because basically the more data you see, the less and less your prior becomes important. Okay. However, I will discuss with you the importance of prior later on in certain assumptions that we're going to make with this likelihood over here, and we'll dig into the math behind it. In certain cases, I believe I'll show you what would be the difference if we had the prior or if we didn't. Okay, but anyways, the whole error function boils down to this. My error equals minus log of the likelihood. This right here, this right here is called my error function, and basically this right here is called the maximum likelihood estimation, right? So basically this is how we jump from maximum posteriori estimation to maximum likelihood estimation. So the only difference between the two would be, so in both cases we can get rid of the probability of observing the observations, basically, but the main difference is that if you ignore the priors, you're basically dealing with only and only the likelihoods, right? So that is when you're dealing with maximum likelihood estimation. Otherwise, if you also have the priors, which I'll show you soon enough, I think in the next videos, in that case you're dealing with maximum a posteriori estimation. Okay, this is great. Now, before continuing, I'd like to focus on one important thing here. So how does the M part of both MAPE and MLE work, that maximization? Remember that MLE and MAPE give us an objective, right? This is an objective function. This right here with MLE is an objective function. For the case of just MAPE that we discussed here, all this guy right here, again, the probability of D can be ignored during maximization. This part right here is an objective function that you want to minimize, okay? They both give us an objective function, but they do not give us a method to basically do the minimization, right? So just as a side note, whenever I'm talking about minimization, I'm talking about the basically minus the log of posterior, okay? If I just say maximization, just have it in your mind that, okay, I'm not talking about the error. Anyways, they're both the same thing, maximizing the posterior or minimizing the minus posterior. They're both the same thing. It's just a terminology thing. Anyways, how can we actually achieve this minimization? So practically performing the maximization or the minimization can be a rough task, and therefore there are different ways to do that, but one of the most common approaches is the gradient descent approach that is quite prevalent in neural networks. Actually, Jeffrey Hinton was one of the people that came up with gradient descent, and when you look at it, it just seems quite complicated and really magical, but if you just dig a little bit deeper into it, you realize that it is basically very simple, but I mean, the way it works is just amazing. There are other ways of optimization, one of which is the simulated annealing, and etc., etc. This course is not done optimization, so I'm not going to dig deeper into these ideas here. Now, as for the last slide of this course, I mean basically of this video, which is only one part of this whole course, I want to talk to you about how we can combine this MLE and MAPE with artificial neural networks, or ANNs. And that is when the idea of supervised learning comes out. Remember that when we're talking about error functions, we are basically trying to measure how well our model is performing, okay? So if we have an artificial neural network, we'd like to use that error function to figure out, okay, this particular artificial neural network with these sets of weights, how well is it performing now? Do we need to tweak the weights? Do we need to learn better? Do we need to change something to make it work better? So that error function is going to give us a measure as to how well or how horrible we're doing, right? So how can we apply MAPE and MLE to an artificial neural network with weights W, right? So here's the tricky part. Let's assume that we have a set of examples, D of I and T's of I, where D of I is the ith input and T's of I is the corresponding target. Okay, so basically what this means is very simple. You have an input layer, let's say X. You have an artificial neural network in the middle, say MLP, multi-layer perceptron, okay? And this guy right here generates some outputs for you, okay? Say a vector of outputs. Let's call that y, okay? So these are, say, the predictions of your network, right? These are the outputs. So we have some, I'm going to put a question mark here, some model with loads of like tens and tens of thousands of weights are here, and they get x as an input and spit out some output, okay? And then these outputs will be compared to your target values, basically your ground truth. So what you should have achieved is this vector, and what you have achieved is this vector. So you need to find a way to basically compare the two to figure out how well you've done, okay? So actually, probably it's a better idea to call this, instead of x, to call this d, right? I think that would be better, because the way I'm using the notation here is using d, so I think it would be better to just use d here. Cool. Now, back to this part, right? So if we assume that d of I and t's of I are my examples, so the inputs and the target values, the ground truth related to that input, basically the corresponding target is t of I, right? So we can rewrite the likelihood as the following. So remember that when we say the likelihood, we mean the probability of observation given my model, right? Remember, if I assume that my model is right, what is the probability of seeing this observation, of observing this, okay? Now, I'm gonna work on the math bit here. If I say that D is actually a set of examples, right? I've got loads of examples, so I'm gonna say that D is actually a set of examples, pairs basically, inputs and the target values corresponding to those inputs. So if I do that, I'm going to replace this pair with the likelihood. So the P of D given M, instead of D, I'm going to put D of I and T's of I given. Now, when I say the model, we always mean the parameters of my model. How confident am I in the parameters that I've learned? Remember, when you were talking about the artificial neural network, and you say my network is learning, you basically mean my network is learning the parameters inside of it. Okay? Right. So given the model, so instead of model, I'm going to put the parameters of my neural network, namely the weights that I'm going to denote as W, right? Nothing magical here, just replaced D with a set of examples. In this case, just example I, okay? Now, what does this equal to? Remember, I'm going to use a mathematical rule here. If I'm assuming that D of I and T's of I are dependent on W, basically, right? Basically, I'm not assuming that, but I'm basically trying to compute the conditional probability of observing this pair simultaneously given my W, given that I have the set of weights W in my model, okay? So mathematically, this would break down into the probability of my target value given my input di and my weights, right? So if I have this particular input and these weights, what is the probability of having this target value, right? Remember that still we have to account for this relation between input and the weights, right? So remember that we will still have this bit here, the probability of input I given my weights. Remember that I'm trying to compute the probability of observing D of I and T's of I simultaneously happening given my W. So t's of I given input and weight multiplied by the probability of d of I given w, right? So the probability that like t of I happens if d of I and w happen at the same time. Now, these guys right here, we have to account for the probability of these guys as well. So, okay, what is the probability of d of I given that I have the w? Remember that w has always been in the second side, in the right side of my condition. Okay, so I have to account for that here. So eventually, remember that this right here, you might have noticed that my input has nothing to do with my weights. What I get as training data has nothing to do with the weights that I have now, right? So we can translate this into just the probability of input I, right? And well, this part remains the same. D of I and W. Lovely. Okay. There's a reason why I'm basically converting everything into a supervised scenario. Remember, when we're dealing with when we deal with terminologies like supervised learning, it means that we have a ground truth during training, right? So for every example, we will have a ground truth value, right? In the next videos, we will talk more and more about this part right here. And we will talk about the different assumptions that we will consider for our likelihood, which could serve different sets of tasks. Namely, if we're dealing with regression, a regression problem, if we're dealing with a binary classification problem, if we're dealing with a multi-class classification problem. So I'm not going to jump into those details now because we have covered enough, I believe. So until our next class, well, take care of yourselves, and I hope that this has been informative for you. So on behalf of MLE, take care.